Hope everyone's doing well and dealing with the with whatever snafus the weather has presented to you. Um, let's talk about direct current circuits, DC circuits. Here's what we're going to be talking about. We're approaching the end of our first module. Our first module intended, and I think it has, intended to examine electricity. We've got this phenomenon whereby a source of EMF can create the flow of charge. And we've talked about how the flow of charge through a resistance dissipates power. We supply power with EMF. We dissipate or use or extract power from resistance, carrying current. So what we're doing is moving energy stored in a source of EMF, like a battery, from there over to this thing that we need to power. We need to supply power to that thing, that machine over there, from the energy stored over here. So that's really the payoff for the first module, getting electricity, A, from where we have energy to where we need it, and B, to do something useful for us. And in this sort of lecture, we're talking about the ways that we analyze and then use what we learn to design good systems for distributing power. How do we get the power from there to here the best way? And how can we sort of assess what's going on? Why do we need to do this? Because we're talking about perhaps complex networks of resistors, batteries, capacitors. So I'd like to have sort of a toolbox of techniques that I can use to approach circuits. We have talked we have talked about the fact that capacitors in series, stacked, and in parallel arrangements have equivalent capacitances, and we've used that to, simplify the analysis of a capacitor arrangement. So let me just remind us of things that we know. The equivalent capacitance of capacitors in parallel is just the sum of the individual capacitances. The equivalent capacitance of capacitors arranged in series is the reciprocal of the sum of the reciprocals. And I'm going to write it this way. Take each capacitance, find its reciprocal, add those things up, and then find the reciprocal of that. Things we knew. What about resistors? We talked about resistors in the last sort of lecture, the last discussion. What if we have multiple resistors? Well, resistors in series can almost think about that like one long resistor, right? I mean, this one has some resistance according to rho L over A. Adding the extra resistor, let's assume that it's the same geometry, just to kind of conceptualize. We're just adding another length. So the total resistance of the whole thing, whoa, all right. It's just the sum. So the equivalent resistance of resistors in series is the sum. And if we're making a comparison, I see these two things. So does that mean that resistors in parallel are the reciprocal thing? The answer is yes. How can we prove that though? Let's consider let's say it's an ideal battery with some EMF. And this is resistor 1, and this is resistor 2. Now, the potential difference across resistor 1 is the current through resistor 1 times the resistance, because resistors are ohmic. And the potential difference across resistor 2, same story. But these two potentials are the same because this point is electrically the same as this point. There's just a wire between them. And compared to the resistors, I'm about to sneeze. Compared to the resistors, the wires are negligibly resistive. Okay, so the potential across, they're equal. Okay. If we talk about the battery, the potential difference, the EMF in the circuit is producing a current, a total current, according to the resistance, the equivalent resistance in the circuit. Now, the current through the battery gets to this junction and splits. Some current is going through resistor R1, this much. Some current goes forwards and goes through resistor R2, that much. But these are charges. However many of them are moving per time, however much current there is flowing through the battery, we only have that much current to work with. We only have, per unit time, that many charges. So if some of them are going through R1 and some of them are going through R2, that's fine, but that's the total. Which means these three expressions, if we solve them for I, now the potential difference across the battery and resistor 1 and resistor 2 are all the same. It's the EMF of the battery. This V is actually the EMF. Divide by the EMF, and the reciprocal of the equivalent is the sum of the reciprocals, which is exactly what we said. Okay, resistors in series and parallel. Fantastic. So if we see an arrangement of resistors, we can simplify it if we can recognize it as series and parallel. We can always. Or maybe we could, but we'd like not to have to. Just now, this statement. However much charge is moving. We're not going to just lose charge along the way, and we aren't going to accrue any. However much charge is moving per unit time, that's how much charge is moving per unit time. And at every spot along the circuit, this has to be true. However much charge we have is in the, consistent in relation with however much total charge we have moving through the circuit. The other thing, as long as we're writing conservation statements, we know that there's a conservation of energy. Right? However, energy cannot be created nor destroyed. It can change form. Energy could be changed into work, could be dissipated into the environment as, let's say, heat by a resistor. The power supplied by a battery is the current times the voltage. the power dissipated by a resistor, which just comes from the fact that the resistor is ohmic. Power supplied. What if there are more? Let's say there are resistors in series. Oops. Three of them. Power supplied by the battery. We have converted some amount of energy from, I don't know, electrochemical stored energy into electromotive force. What happens to it now? Well, it's got to be either remains in the circuit and is permanently energized, perhaps because we're charging a capacitor, or it gets transferred out of the circuit as heat or some other sort of thing, some other sort of conversion. We do work on some motor to turn it or something. But however much energy we've sort of transferred, we need to transfer that much again. So that this equal sign, that's the conservation of energy. So that thing that I wrote, that the equivalent resistance, it actually comes from the fact the equivalent resistance of resistors in series is the sum. That's conservation of energy. And these two ideas form the basis for Kirchhoff's rules of circuit analysis. There are two. There's the rule about a junction. Anytime we have two paths or more, leaving from one path coming in, or vice versa. The total current coming in has to be equal to the total current going out. That's what we said. In any loop, anytime we start from somewhere, get back to someplace, that's the same spot. It should have the same electrical potential. So we should net zero change in electric potential. So, well, yeah, the sum, the net potential difference around the loop has to be zero. Conservation of charge and conservation of energy. Not new. We credit them to Kirchhoff because, I guess it was Kirchhoff that first published their use for analysis of circuits. But yeah, these are familiar ideas. Resistors in series. We knew this already. Resistors in parallel. We know this already. When I post the slides, check out this link. What does it mean, sort of practically, that resistors in series add resistances? Well, it means that the current flowing is less than it would be through just one. What does it mean if resistors are in parallel? Actually, it means that the equivalent resistance is less than the resistance of any one of the resistors. Which means the overall current in the circuit would be greater. And that's why the bottom bulbs are brighter than the top ones. Does that make sense? Just now I'm thinking of this, like, remember back in, I don't know, back in like high school, you had these math problems that where like there's a lawn that it takes an hour for, person number one to mow, and it takes 2 hours for person number two to do it. How long does it take them if they work together? Stuff like that. That's like parallel. That's like resistors in parallel. There's a job that needs done. We've got to get charge from point A to point B. If all three of these resistors work together, that's better than if only one of them does it. R1, it's going to take some amount of energy to move charge through R1 only. It's going to take some amount of energy to move through R2 only, through R3 only. But if we have all three, there's 3 different ways to move energy, like 3 different people mowing the lawn. It's going to be easier. It'll get done faster. Overall, we'll need less energy to do it. Which is true. To move a particular current through this arrangement requires less EMF because the equivalent resistance has decreased. All right, so what's the story here? Yeah, there's still 3 resistors, but now we can't do them. We can't work on the job all at the same time. One person's got to do it, and then the next person's got to do it, and then the third person's got to do it. The whole job. This is going to take more energy altogether. Certainly going to take more time to mow the lawn. I don't know why we're doing it all, 3 people mowing the lawn, one after the other. Probably not great for the lawn, but maybe that's not the best example task to perform. Come on. There we go. Series versus parallel, and all right, what if we have both? Series and parallel. Well, R2 and R3 are in parallel. We know that because this point and this point are the sort of terminal locations for this path and for this path. It's the same point though, so the potential difference across them is equal. If the potential difference across 2 resistors is equal, then they're in parallel. That's kind of what that means. So R2 and R3 are in parallel. We can use the parallel sort of equivalent replace this with one equivalent resistor, which is in series with R1. And okay, we can combine them, and then we go. Same story here. We could combine these two as one REQ, and then that's in parallel with R1. Kirchhoff's rules allow us to handle circuits that are not quite so straightforward. In general, the potential difference across none of these resistors is the same, including the internal resistors in the batteries. Also, in general, the current through any of these paths is not the same. So, not the same current, not in series. Not the same voltage, not in parallel. That's fine. We still have charge and energy conservation. Any closed conducting path. Check out this link when I post the slides. We're going to practice Kirchhoff's rules applied on Tuesday. That'll be part of Tuesday's recitation. If, as we're traveling a particular loop, not as the current is, but as we considering a loop, as we are moving around the loop, we might be moving around the loop in the same direction or the opposite direction to the current. Here are our conventions. If we are moving through a battery, through an EMF, from negative to positive, let's, in our summation of potential differences, we'll call that a positive term. If we're moving the other way through a battery, we have to treat it like a negative term. And that's only it as we go from negative to positive, the positive terminal has a positive potential difference with respect to the negative one. So our potential, electric potential, has increased. That's delta V is increase. If we go to the other way from positive to negative, well, the negative plate or the negative terminal has a lesser electric potential than the positive terminal. Okay, so our electric potential has decreased. If we are traveling through a resistor in the same direction as the current, we spend energy to do that. The electric field set up in the wire created by the EMF does work to move current through a resistor. Work done transfers energy out of the system. Our electric potential, energy per unit charge, must have decreased. If we go the other way, though, it's positive. Two batteries, each with an EMF and an internal resistance, and two resistors. The wires, let's say. A little bit of internal resistance just to kind of keep things safer when you're jumping into a battery. Using Kirchhoff's rules, we can find the current in the circuit, the potential difference, and the power if we're going to do this, we need to be able to measure things. All right. Don't pay too much attention to the schematic here. We're relying on things that we don't know about yet. Just know that the greater the thing we are measuring, the more the deflection from zero against a spring, which tends to push it back. This is called a galvanometer, and we could use them to make either an ammeter or a voltmeter. We put the ammeter right in the circuit. It is required to complete the circuit. In other words, we've got a circuit, we break it and then use the ammeter to finish it again. A voltmeter, the circuit element is down here, and we connect into an already running circuit. The circuit would be going, charge would be flowing without the presence of the voltmeter, which is why we often measure voltage sort of preferentially, because I can assess this without breaking shit. If there's a current in the circuit that I need to measure, I have to break the circuit to put the ammeter in. Voltage I can measure from outside the circuit. If we're doing both, note the internal construction. Each of them has a resistor. And the presence of that resistor in the voltmeter, say, is going to affect the reading by the ammeter. It's going to affect the current flowing through that particular branch, because some of it will have diverted this way. And either way, unless the corrections are small, now what would that mean? If the resistance of the voltmeter is very, 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 very high, the current isn't going to prefer to go this way, because there's a lot of resistance that way. Most of the current is going to go this way through the ammeter, which is where we want to measure it. If the resistance of the ammeter is very, 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 very low, then from B to C, there's very little potential difference, which means the voltmeter can measure actually the potential across the resistor. So voltmeters, we want resistance to be very high. Ammeters, we want the resistance to be almost zero. Can't be zero, but it should be low enough that we're not spending very much energy going through it. And the resistance can't actually be infinite, then it won't measure anything, but it should be large compared to the resistance elsewhere in the circuit, so that we're not incentivizing the current to flow through the voltmeter as opposed to whatever resistor we're trying to measure. To use the ohm meter, first connect X directly to Y. And adjust until the meter reads 0. Then connect X to Y through the resistor R. The equivalent resistance will change, which will change the response from the circuit. Or we can use a digital one. And we can measure voltage, current, resistance, as long as we've connected it properly. Note, there's no circuit here. If we're going to use an ohm meter to measure resistance, I don't want there to be current flowing in it, because that's going to affect things. Because of the way we need to sort of calibrate the ohm meter, the only current we want to talk about is the current from this EMF, not from some other circuit. So an ohm meter wants to measure resistances out of circuit entirely. An ammeter, current meter, wants to live in the circuit, wants to be part of the series connection. A voltmeter can measure across an existing circuit element from outside the circuit. Potentiometer is a term for a variable resistor, like this one. Or here's another version of the same symbol. I was always a little bit curious why a variable resistor was called a potentiometer. And the reason is that it is used to measure an unknown resistance by comparing potential differences. Actually, what we're doing is measuring the potential across a particular resistor. And then using that and what we know about resistors, that they are ohmic, to talk about the resistance. Or, yeah. All right. One of the sort of common applications of capacitors that's talked about a lot in physics textbooks is charging the flash of a camera. Not so much of a camera phone. Sometimes that's the same sort of deal as the flashlight. But if you've got a camera with a flash, that bright light that's created is a rapid discharge of energy. More rapid than makes sense to be supplied only by the battery. Because remember, the greater the current through the battery, the less potential difference we actually get because we have to spend more energy pushing through the internal resistance. The less potential difference, the less energy per unit charge, and the less bright is the flash, because we're talking about a decreased transfer of energy. Okay. So we can use a capacitor. The capacitor, instead of a resistor that dissipates the energy right away, or uh, a motor that, again, dissipates the energy right away, transfers the electrical energy that we're talking about into mechanical energy, we could ask the battery to provide EMF in order to store the energy in a capacitor for rapid use later, or for any use later, but use maybe that the battery is less well suited for. We start with an uncharged capacitor connected in series with a resistance and an EMF. Initially, there's no current flowing because this isn't a circuit. Initially, the capacitor is uncharged. Neutral plates. We close the switch. The EMF is able to move charge because we've given it space to do that. Positive charge carriers would be pushed away from the positive plate and pile up on the left plate of the capacitor. Positive charge carriers would be removed. They have to come from somewhere. They would be accelerated through, pulled through the EMF of the battery. And that means that we're dragging them from here, moving positive charge carriers away from the right-hand plate of the capacitor, leaving it negatively charged. As we do current, we charge the capacitor. Let me say that again. As we do current, we charge the capacitor. Every small amount of time yields us some new amount, dq, piling up on the capacitor plate. Okay. As there is current, we've got the EMF of the battery, we've got the resistor, which would, as we follow the current around, the resistor, as current exists, would tend to, I'm thinking about the loop rule here. So if I'm going to start from here and walk around the loop to the left. First thing that happens is we encounter an EMF. Then we have to go through the resistor in the forward direction. Then we have to go through the capacitor. Now, as it is charged, there's a potential difference between one plate and the other. That potential difference, it starts to look like a battery, but the positive plate is on the left. The capacitor, as it charges, tries to push back the other way. When fully charged, no current flows anymore because the EMF and the capacitor have equal potential differences. Each of them is trying to move charge, but they're equally strong, so we go nowhere. At any given time, the charge across we're doing voltages because this is loop rule. At any given time, the voltage across the capacitor, C equals Q over V, so V is Q over C. And I'm going to draw it with a minus sign because imagine it's like a battery. As we finish walking around the loop this way, we're going from a positive plate down to a negative plate. That's a potential decrease. We get back here, and if the switch is closed, then we're back and we can do that again. Now, I, the current, is related to the actual charge on the capacitor. And we have a differential equation. We'd like to separate this and get the Q's on one side and the DT's on the other side. Let's see. dq dt r. The EMF, though, is the total potential difference that will exist across the capacitor. When it is fully charged, I'll use capital Q for the full charge. So that's 1 over capacitance, Q minus Q. Now we've got a factor that only depends on Q that we can combine with the dQ. And a term that we can combine with the dt and integrate. I'll leave the integration to you. I think U substitution will work here. Keep track of the minus sign. We're going to need it. That's my capital Q, and I think we end up here. Nope, I lost the R. Yeah, it's got to be down here. And that product RC, that shows up in our solution. Parameter of an exponential function. It talks about the time during which a factor 1 over e occurs. Once we have the charge on a charging capacitor as a function of time, we could differentiate to find the current. We could multiply this equation by the, let's see, we could divide this equation by the capacitance to talk about the potential difference across the capacitor. Here we do the differentiation, and we end up with a maximum current at the beginning and an exponential decrease as charge builds up on the capacitor, which makes sense given what all we've talked about. What if we have a charged capacitor and we'd like to discharge it? Okay. We need to make ourselves a different circuit without an EMF in it. And actually, we're going to pretend like the capacitor is the EMF. It's going to have an EMF that decreases as it discharges. So again, let's start with no current. Let's start with an open switch and a charged capacitor. Close the switch. The charged capacitor has a potential difference. That potential difference it functions like an EMF, creates current. A little bit unsure of the direction of the current. I think it would be the other way. But the reason these arrows are drawn the way they are is so that they point in the same direction as these arrows. So the current as we were charging the capacitor was counterclockwise. So we continue considering a counterclockwise direction. We get an exponential decrease from, which makes sense, I think. It was an exponential increase. And if we take the derivative, we end up with this expression. Which I think, makes a good deal more sense. Current is scalar. I guess we could talk about current one way or the other way as positive or negative, but I'm still a little bit uncomfortable with that. The current has a magnitude. It is largest right at the beginning when we start to discharge, and it decreases exponentially. It actually flows in the other direction. The current, as created by the capacitor, actually flows this way. Does that change anything about the actual when we take this derivative, we get this minus sign. And I guess that minus sign was going to happen regardless. So accounting for the minus sign just means the current is going the other way. It is what it is, I suppose. All right, we take the derivative of this with respect to time, we're going to get a negative 1 over RC. Now, if we think specifically about the charge on the capacitor, dq is a negative. It's a negative quantity because we're decreasing the charge on the capacitor. So we could use that minus sign and then talk about the unsigned value, the magnitude of the charge dq, to sort of straighten out this minus sign, but it's not. Either way, we have to do a little bit of sort of conceptual work to make sure we understand that the charge on the capacitor is decreasing because it's sort of causing current the other way, the way opposite it was used, the opposite direction of the current that was used to charge it. That's all that minus sign is doing. As long as we can handle that minus sign, sort of abstractly from as long as we can bring that with us, then this is enough. We need the magnitude, and it decreases exponentially. Just giving you a minute to take in this diagram. Imagine this is one room of the house, and this is another room of the house, and there might be more rooms. This just ends. Maybe at an outlet. I don't actually want current to flow like that. unless there's an outlet there. I want to set up a potential difference between the top and bottom so that if I close a switch, if I plug something in, then I can get current to flow this way. But if these outlets remain unplugged, that no current flows through them, and that doesn't affect the current through the light that I just tried to turn on. So we have a main fuse in series with a parallel arrangement of multiple fuses, one for each sort of circuit that the house is constructed on. Each of those circuits, the all the outlets in the kitchen are on the same fuse, let's say. And all those outlets are in parallel with each other on that same sort of line, on that same circuit. A fuse, if the current gets too large, the power dissipated by that element is large enough to melt the conductive element and the circuit's broken, which saves your devices from melting themselves. A circuit breaker, maybe a little bit better, is a electromechanical device that does the same thing. If the current exceeds a particular value, it flips, turns the switch off, and breaks the circuit so that we avoid frying any devices. A blown fuse, this happens in the car. Sometimes you got to replace the fuse for the headlights or whatever. Blown fuse needs to be replaced. The multimeters, the digital, voltage, current, ohm meters in the lab on campus have fuses inside. If you try to measure too much current, it'll blow the fuse instead of frying the electronics. So if you find a voltmeter that doesn't quite work, maybe that's it, and the fuse has to be replaced. A circuit breaker, like are in houses nowadays, has an advantage that we can reset it after they were tripped. What's the third prong for? Got my Mac charger deal here. This has 2 prongs. What's the third prong for? If we look at the diagram, we've got a line of hot line of positive potential difference relative to the neutral line. That's all that means. So 2 lines is all we need. 2 prongs. What's the third one for? Suppose you have a device that makes an accidental electrical connection with the, maybe it's a hairdryer or a drill or something. This one's a drill. Suppose we accidentally make an electrical connection with the housing of the drill itself. The power supplied might be communicated through the housing of the device and can't get maybe back to this line. That circuit's broken, so it's going to travel through the next thing that it can, and maybe that's you, which we'd rather not happen. The third prong is an extra bit of safety. Even if that same electrical connection is accidentally made with the housing itself is grounded, there's an additional path not through your hand that allows, even if something goes wrong, that allows for safety. The current isn't going to flow through you, it's going to flow through the ground connection. That's all I got to say. On Tuesday, we will practice. Thanks, everybody.